This video is going to show how to model impedance with analog behavioral models in PSpice. Analog behavioral models, or ABMs, are used to define sets of electronic components mathematically. The Laplace ABM provided in PSpice allows you to quickly and easily model impedance or admittance to expedite the design and testing processes. We'll demonstrate by creating a new design in PSpice Designer. Select File, New, Project from the menu. The New Project window opens. Enter a name for the project. We'll call ours ABM Impedance. Select the ellipsis under Location and browse to the working directory to save the project. Ensure Enable PSpice Simulation is checked and click OK to create the project. The Create PSpice Project window opens. Select Create a Blank Project to create a new schematic and click OK. The Capture Schematic canvas opens. We'll start by placing the analog behavioral model. To place a component, select Place Component from the menu. The Component Explorer tab opens. Here you can place PSpice components as well as predefined components from UltraLibrarian, Symaxis, and your personal workspace. Expand PSpice, Source, Controlled Sources, and select Current Source. A list of current sources opens. Select G Laplace to place a Laplace-dependent voltage-controlled current source. A preview of the model appears in the Symbols and Footprint subpanel. Impedance can act like a voltage-controlled current source. The current between its output nodes is a Laplace function times the voltage across its input nodes. If the input and output nodes are connected, the source acts as a behavioral model of a resistive or reactive circuit. Double-click to attach the model to your cursor. Click to place the model in the schematic, then right-click and select End Mode. Now let's create a circuit around this behavioral model. We'll start by placing a voltage source. Select Place, PSpice Part, Source, Voltage Sources, DC from the menu. Click to place the voltage source, then right-click and select End Mode. Select Place, PSpice Part, Resistor from the menu. Click to place the resistor, then right-click and select End Mode. A PSpice ground object is required for simulation. Select Place, PSpice Part, PSpice Ground from the menu. Click to place the ground at the bottom of the circuit, then right-click and select End Mode. To wire the circuit, select Place, Wire from the menu, the Wire button from the toolbar, or press W on the keyboard. Click to start drawing the wire from the source to the model and click again to finish. Click each component endpoint to wire the schematic. When finished, press Escape on the keyboard to end wiring mode. Before we simulate the circuit, we need to define the source voltage. To do this, double-click the value in the schematic canvas. The Display Properties window opens. Enter 5 volts for the value and click OK. We are now ready to create a simulation profile. Select PSpice, New Simulation Profile from the menu. The new simulation window opens. Enter a name for the simulation. We'll call ours ABM Bias as we are running a bias point simulation. Click Create. If the Simulation Manager Product Choices window opens, select the appropriate license and click OK. The Simulation Settings window opens. Here you can define the type of simulation to run, its parameters, and any additional simulation options. Select Bias Point for the analysis type to run a bias point analysis. Leave the default settings and click OK to create the simulation. Select PSpice Run to start the simulation. The PSpice AD window opens but remains blank. Plots are not shown or used for a bias point simulation. Back in the schematic canvas, select Enable Bias Voltage Display from the toolbar to show the steady-state voltage at each node. Select Enable Bias Current Display to show the steady-state current at each node. With pure DC, the default Laplace model acts as a short and the resistor draws 5 mA. Let's model capacitive impedance to block DC. Double-click the Laplace model to open the Property Editor tab. This tab shows all properties of the Laplace model in tabular form. The X-form row lists the Laplace expression that will be applied to the current output. Double-click the cell and enter 1n times S. This will set the model admittance to 1 nano times S, or the impedance to 1 over 1 nano times S, simulating a 1 nanofarad capacitor. Click Apply and close the Property Editor tab. To rerun the bias analysis, select PSpice Run from the menu. Close the PSpice AD window if it opens. The current through the load resistor is now close to 0 amps as the capacitive model is blocking DC. Now let's run an AC sweep analysis on this impedance ABM for better accuracy. To do this, we need to place an AC source in the schematic. Select V1 and press Delete on the keyboard to remove it. Select Place, PSpice Part, Source, Voltage Sources, AC from the menu. Click to place the AC source where the DC source was in the schematic, then right-click and select End Mode. Next, we'll create an AC sweep simulation profile. Select PSpice, New Simulation Profile from the menu. Name the profile ABM AC and click Create. The Simulation Settings window opens. Select AC Sweep Noise from the Analysis Type dropdown. Enter 100 for the start frequency, 10 meg for the end frequency, and 10 for the points per decade. This will start the sweep at 100 Hz, finish at 10 MHz, and divide each decade into 10 points. Click OK to save the settings and close the window. Unlike bias point analysis, AC sweep analysis will plot the circuit output at each calculated frequency. To indicate the circuit output, a probe must be placed on the schematic canvas. Select the Voltage Level Marker button from the toolbar. Click to place a probe at the output of the current source model, then right-click and select End Mode. Select Enable Bias Voltage Display and Enable Bias Current Display to disable the bias displays. To start the simulation, select PSpice Run from the menu. The PSpice AD window opens to show the plot. As expected, the voltage across R1 increases as frequency increases. Close the PSpice AD window. Now let's simulate a bandpass filter consisting of a capacitor and inductor in series. The impedance of such a circuit can be expressed as this equation. Double-click the X-form value and enter 1 over the equation to define the admittance. In this case, we'll simulate a 47 microhenry inductor and a 100 nanofarad capacitor. Click Apply and close the Property Editor tab. Select PSpice Run from the menu. View the simulation results. The load resistor receives full voltage between approximately 10 kHz and 500 kHz. Quickly model impedance with analog behavioral models to ensure accurate circuit behavior with PSpice. For more tutorials, visit us at resources.ema-eda.com and don't forget to like and subscribe to our YouTube channel.